Anybody have any questions, feel free to ask me. I'm just now getting everything up to speed. More. Got about 2 minutes left, everybody. Feel free to ask me any questions. I'm just getting prepared. All right, got some more people coming in. People coming in. All right, just about time for class to start. Anybody have any questions about anything in the past so far? Any past homework problems, anything like that? Hopefully everybody knows you. I've got a test due this Sunday. That's test 7 that covers chapters 9 and 10. Probably next week I'll put up a test 8 that'll be online, and that'll cover chapters 11 and 14. And that's about it. But I just want to make sure everybody's up to speed on that. So everybody remember, you got a test this Sunday. You got to get it done. If you've missed any tests, now might be a good time for you to let me know, and maybe I'll be nice and let you guys make it up. The online test, that of course, if it's a face-to-face test, then I'll also be kind enough to let you make it up. But I'm going to have to get you to do it at a testing center or something. So, anybody have any questions before we move on? All right, so we have now completed chapter 11. That's what we did last time. And we're going into chapter 14 and 15. And that, depending on how I choose to use my lab time, which also agrees with how your lab time is used by your lab instructor, we might actually cover some more material. In other words, I might actually go ahead and cover relativity. With you guys, since I can't really put that on the teachers unless the lab teachers want to do it, I probably wouldn't do that to them, but I could make it where y'all can watch videos and that would account for your lab time, and that gives them the time off. So that's possibly what we're going to do. And of course, I'd still be available to answer questions and stuff like that. So hopefully I can still get in 14, 15, and 36. If I don't get in 36, then 36 will be an extra credit homework set, as is 12, chapter 12, chapter 13, and there's some chapters in the 40s that are extra credit, and those will all be due probably by like the 4th or the 5th of December. I don't want it to be due the last day, but I also don't want you to have it done now. So anybody have any questions on that before we get moving? Okay, looks like everybody's good to go on that. I got no chats, I got no comments. Looks like I got 12 of you in here. So chapter 13 is on oscillations, and you'll notice that the word is oscillations. I've heard people mispronounce this before, and of course I'm all about a good, thorough, well-rounded education, so I don't want you guys mispronouncing it, but at the same time I also want you guys, like myself, to be very kind to people when they mispronounce words, because that normally means that they've learned a word from reading as opposed from hearing it from people. And that's a pretty brave thing to use words that you've learned in reading when you actually haven't heard them. So the word oscillation does not have a loud or soundful C. It's just a C that's in there sort of historically, but it's oscillations as if it's just OSILLATIONS. And that just basically means a vibration or a back and forth motion. And what we're studying here is periodic motion. And periodic motion is any motion that basically repeats itself. So if you have a X versus time that goes down, up, down, and then slowly like that for some period of time, and then it repeats itself, even that complex down, up, down, and then slow, even that is repetitive, and therefore it's really a repeated motion and periodic. So the period is what we define as the minimal time required for it to repeat whatever that smallest subset of the motion is. So we're going to talk about that as well. Let me go ahead and share my screen with you guys so I can talk a little bit more about this with some, instead of hand gestures, with some actual stuff written on a document. So for instance, you might have, let's say, a coordinate on a coordinate system, you might have a graph that is the x position as a function of time, like this. Actually, I did a really bad job on that t there. As a, well, okay, as a function of time. And it might do something like, and then repeat itself. Like that. Okay. In that case, basically what we're saying is from here to here is t, which equals the period. That's the smallest amount of time over which the thing repeats itself. Here's another one. Here's another one. So it doesn't have to be some really simple motion, but it can be. So for instance, another periodic motion might, for instance, be something that you're probably a little more familiar with. Okay, and this drawing obviously is not going to be perfect, but again, in that case, you can see that this motion repeats itself, and it seems to repeat itself here, and then again by here, and then again by here, and again, this distance in time, again, I would put the distance word in air quotes, but that distance over time is the time required for it to complete one period. And therefore that time is also called the period. So whatever the smallest unit of time is that it can repeat itself, that's called the period of motion, and it's normally measured in like seconds. Okay. So for instance, let's imagine for a second that we're standing on a pier and we see ocean waves coming in, and they're nice, smooth ocean waves that are very repetitive. One looks just like the other. And what you do is you have a stopwatch and you see the peak of a wave arrive under you. So let's say you're on this pier here like this, something like that. And what you see is this particular wave right here has a peak that's right under you right now, and you say t is equal to 0. And then you wait sometime later, and you wait sometime later until all of a sudden now this peak right here is under you. So now what's happened is this peak has now moved to right here. So that is t equal, let's say 8.0 seconds. So that would mean the wave has a period of 8 seconds. So basically what happens, you're standing on the pier, the crest of one wave comes by you, and you start your stopwatch. That's t equals 0 seconds. And then you wait, and the crest of the next wave gets right under you, and you stop your stopwatch, and it says 8 seconds. So this would imply t, which is the period of the motion, is equal to 8.0 seconds. Now, I might ask you, how many, and I'll say r, what fraction of waves passes you in 1.0 seconds? Can anybody tell me that? So we found the wave has a period of 8 seconds, and I'm asking you how many waves will pass you by in a single second.
1/8 of a wave?
Exactly. The answer is 1/8 of a wave. And that's not coincidence, by the way, the fact that the period is 8 seconds and the frequency is 1/8. In fact, that I just tipped my hand a little bit, but frequency, frequency, frequency is defined to be the number of cycles that occur or transpire. Somebody just came in, hold on. In 1 second. Oh, left off a D there. And number of seconds. Okay. So for instance, what we've just discovered is that the frequency of this wave is equal to 1/8. And I'd say that cycles per second, which we can also write as 0.125 because we know that 1/8 is 0.125 or 12.5%. That's also equal to 0.125 CPS. So a lot of old manuals from the military, for instance, will say CPS. But another way of writing that is 0.125 hertz. And 1 hertz, named after Heinrich Hertz, is the abbreviation for a cycle per second. And it's abbreviated by capital H, lowercase z. I don't know what just happened there, but that's not helpful. Okay. But now I can't get this thing to stop making a stupid text thing. Ugh. Okay, I've got rid of it now. Let's see if I can do this. Okay, now I'll move it over here and then hopes later that I can delete it. All right, so the abbreviation I was trying to write before I got so rudely interrupted by this technology. So that's 1 hertz is equal to 1 capital H lowercase z. That's the main thing I was trying to show you there. And now I'm going to try to delete that. It did work. So this is not a happenstance. In fact, the thing that we just learned is that the frequency is 1 over the period, and the period is 1 over the frequency. And you also know from rotational motion that there's something else called the angular velocity, which we can also call the angular frequency. So omega equals angular velocity or angular frequency. And that's what we're using here is the angular frequency. Okay. And that is defined to be 2 pi times the regular frequency. And you can probably realize that 2 pi is just basically converting cycles per second to radians per second, because that's the units of the angular velocity as well as the angular frequency. Okay, so those are 3 of the major things we're going to be using in here. Another thing we'll use is, at least in sinusoidal motion, which is what we call simple harmonic motion, there is a concept of drawing up from the midline to the peak or down from the midline to the trough. That distance is called A, and A is defined to be, anybody know the name of that? I bet you do.
Amplitude.
Yes. So that's another variable we're going to use, and I want to make sure everybody followed that. Okay. So those are some of the terms that we're going to use. Frequency is measured in hertz. It's 1 over the period. Period is measured in seconds. It's 1 over the frequency. Angular frequency is omega, and that's 2 pi times the frequency. And then amplitude is sort of the half of the distance from the top of the peak to the bottom of the trough, measured vertically, measured in fact perpendicularly to the way the thing appears to be traveling. So with all that in mind, we've got sort of everything we need to know here. What we do know also is that if you want periodic motion, which is the predecessor to what I'm calling simple harmonic motion, then periodic motion requires a very specific type of force. So periodic motion requires a force that always brings the moving object back to where it started. So, for instance, Robert Hooke gave us a particular force that works, and it's called Hooke's law. So, for instance, Hooke's law, dang it, Hooke's law. Now, Hooke's law is, we use it in physics a lot for springs, but to be honest with you, it's for anything. It's basically any solid object is going to exhibit this behavior. And the behavior is that the force that the solid object, whether it be a spring or a piling or a 2x4 or a rod or whatever, and whether it be a string or excuse me, a rod in tension or a rod in compression, doesn't matter. But basically what it says is that the spring or the object, the rod or whatever, will apply a force that's equal to negative times some constant times the distance x that it's been stretched from equilibrium or compressed from equilibrium. So this is x is the distance from equilibrium. And in fact, what you're doing is you're trying to imagine this x being say along the x-axis, where you'd have the origin of the x-axis exactly at the equilibrium position. Therefore, when you pull it to the right, if you assume the right is the positive x direction, then your x position of the object will be a positive number, whereas if you pull it to the left, your x position will be a negative number. And the reason why that's important is because in order for you to have the periodic motion that requires a force that always brings the moving object back to where it started, oops, I just realized I didn't finish the word started. Then you need a force that always pulls the opposite direction of the displacement. So in this case, you look, if x is a positive number, then f is a negative number. That means the force is pulling in the negative direction when the object went in the positive direction. Also, if you plug in the x, for the x, if you plug in a negative number, that means you've moved it to the left, and the negative times the negative gives a positive, which means the force is trying to push it back to the positive side. In other words, back to the equilibrium. So that's really what's necessary for a periodic motion, is to have some kind of restorative force like that. And your book actually does some pretty nice little ideas. It asks you things like which one of these forces could be restorative. So let's look at that. So which forces, and actually I'm gonna try to use the same wording that they use. I'm trying to remember. I think they used it as a simple harmonic motion thing or something like that. Let's see. And of course, I'm not going to be able to find it now. That's certainly the case. Oh, that's not it. That's not it. I'm actually just flipping through the book to try to look for that particular conceptual example, but I'm not seeing it. It might have actually come earlier than I'm remembering, which is why I can't find it now, but let's see. No, that's not it. That's not it. So it's definitely not there. Let's see. I don't think I can go any earlier than that, though. Nope, I can't. All right. So some examples that you might want to apply, say, which forces can cause simple harmonic or sinusoidal motion. So what about F is equal to negative 13 x squared. Will that work? What do you think? Anyone? No, the person came in. No guesses on that one?
I would say no, because the square will always make that positive.
Exactly, because if you put it in a negative x, then you square it, that's going to become positive. So what this is making is anything when you move an object to any position x, the force is always going to push in the negative x. So you're absolutely right. This one's no. How about this one? How about y equals negative 3, or f equals negative 3.7 y?
Yes, that'll work.
Yeah, that works. Don't get caught up on symbols. And for instance, the x is what we use in Coulomb, in Hooke's law, but in this case we're using y, and that's perfectly fine as well. So yeah, that works good. What about
You wrote no.
oh, I even changed the color so I would distinctly show that it was something different, and I wrote no. Thank you for that. Okay, so yes, it's a yes. How about f is equal to, let's say f is equal to 6.9 x. Any idea on that one?
No.
Yeah, that would be a no on that one as well. And that's because it doesn't have the negative. You need the negative so that if the x is positive, it's going to pull in the negative direction. If the x is negative, it's going to pull in the positive direction. All right, let's try one more. And let's say f is equal to negative 7.2 theta. Now, this could be theta like you might have done in your labs, or you might be doing in your labs tonight with the pendulum, where theta being 0 is the pendulum string hanging straight down. If you pull it this way, it's a positive theta, but if you pull it this way, it's a negative theta. So this is a case in point of that. What do you think about it? Does it have the ability to make simple harmonic or sinusoidal motion?
Yes.
Yep. So again, it doesn't necessarily matter what the variable is, or if even the variable is not measured in meters, the variable could be measured in degrees or radians or something like that. So that's a key point. So we've got a little bit of an understanding of sinusoidal motion and stuff like that. So let's see if we can answer a couple of other concept questions or exercises. So a mass is oscillating on the end of a horizontal spring. The mass slides on a frictionless surface. Where, if anywhere, does the mass experience 0 acceleration? Anybody have any idea with that? I'm going to call this part A, part B, and part C. Now, we don't have, in general, an equation that you guys know of for a mass on a spring oscillating back and forth. We don't have an equation for that acceleration. But do we have an equation that gives us acceleration? Go ahead, Brandon.
I was just gonna say, would it be at the endpoints?
At the endpoints, you'd say the acceleration is 0. Well, that's actually exactly what I expected everybody to say, and it turns out it's actually not correct. Here's the reason. From Newton's second law, so let's start about with part A. Newton's second law, we say the summation of the forces is equal to mass times acceleration. And sometimes we actually have to put the acceleration as dv over dt or d2x over dt squared. But sometimes it's just a constant, in which case you could just leave the a there. But the main thing is the net force acting on the system is equal to mass times acceleration. So the acceleration is the net force divided by m. So what would the force be on an object when the acceleration should be 0?
0.
Right. So if the net force is equal to 0, then A is equal to 0. So if you're looking, for instance, at a mass on a spring on a horizontal surface like this, what you're saying is there's our spring and there's our mass. And let's say this right here is equilibrium. If I pull the force to the right, you can see there's a force pushing up. It's the normal force of the table, but there's also an mg pushing down, and that should exactly cancel it out. And there's no friction. So really the only forces that could be acting on this is the force due to the spring. So if right here at this equilibrium position, since it's in equilibrium, the F is 0. So yeah, it should actually occur when the stretch of the spring is 0. So when spring is at equilibrium. Okay, does that make sense to everyone? Do y'all agree with that answer? Now, maybe this will be a little bit better one for you. What about when is the velocity 0? Is there any place in this motion? The spring is going to oscillate back and forth, which I can show with this little arrow and this little arrow and this little arrow and this little arrow. Okay, it's going to oscillate back and forth. So can you tell me a time when the actual velocity would be 0? Bet your Brandon's got this one.
Is that at the endpoints?
Yeah, there you go. When at the endpoints. So very good.
Would that be half of the period?
Yeah, it would basically happen like if you made a graph of position versus time, x versus t like this, then you might say the graph looks something like this. All these little dots here would be v equals 0. But I think you can see that that's the case because the derivative of x with respect to time is actually the velocity. And you can see that the slopes here are 0 at these points. So clearly the velocity is 0 there. Does that make sense? Now it's weird. Truly the velocity there is 0, but the force is actually a maximum. That's when the spring is either stretched the max amount or compressed the max amount. So yes, the answer is at the endpoints. Anybody have any questions on that? Got another person coming in. All right, finally for part C, it says the potential energy. So I'm talking about not the potential energy of gravity because this thing's actually horizontal. So we must be talking about the potential energy of the spring. So can anybody tell me when the potential energy of the spring is 0? Remember the potential energy
At
of the spring.
equilibrium?
There you go. So U is equal to 0 when when X is equal to 0, which implies at equilibrium. Okay, so that's it. Good job. Any questions on that? All right, how about this? If an oscillating mass has a frequency of 1.20 hertz, how long will 200 oscillations take? Anybody have an idea on that one? Okay, remember what I told you about, for starters, the frequency. The frequency is the
3
number of
minutes.
cycles divided by the time. Go ahead. I heard somebody say something, so maybe y'all came up with it.
Oh, so if hertz is a oscillation per second, then wouldn't it be 1.2 times 200, which would be like 240 seconds?
That sounds about right. So let's work it out. And here's another way. What he's talking about works really well. What we know is frequency is equal to number of cycles divided by time. And for that, we know that we have 1.20, which works okay, but I think that's better written as 5/4, excuse me, as 6/5. So I'm going to write that as 6/5 is equal to, now I know that has to be the number of cycles divided by the time. So what this says is we can get 6 cycles done in 5 seconds, and that's the same as 1.20. Does everybody understand that 6/5 is the same as 1.20? So another way we can do this, and what the fellow student said was right, but what I can do is say, well, I want the number of cycles to be 200, and I want to know what t is. So whenever we have, in this case, these are actually two rates equal to each other. Remember, a ratio is when a number is divided by a number in a fraction. That's what a ratio is. But the two numbers either have to have no units or they have to have exactly the same units. If you have two numbers in a ratio like that, but they're both what we call denominate numbers, numbers that have units, then if they don't have the same units, then that ratio is no longer called a ratio, it's called a rate. So we can set the two rates equal to each other, and that makes a proportion. And the way we solve a proportion is we cross multiply, and we get 6 times t is equal to 5 times 200, and 5 times 200 is 1,000. So we can see t is going to be equal to 1,000 divided by 6. And 1,000 divided by 6 is 166. I think what you had to do, yes, you had to divide 200 by 1.6. I think you had said multiply 1.20 times 200, but really the answer should be you ultimately would divide 200 by 1.2. So let's see if that works. Yeah, that gave me the same answer. So that's basically what we did. So everybody understand how that one worked? So that's something that we can do over and over. Sometimes you just look at the units of a quantity like frequency, and you know it's the number of cycles in 1 second, but that's exactly the same as saying the number of cycles in any number of seconds, because ultimately you can divide the top number by the bottom number, and then the bottom number just becomes 1. So that's the same thing as hertz. So keep that in mind when you're solving physics problems, is sometimes you can just compare units to units and find a way to get an answer, especially if you don't know how to do it at all. That's a really good choice of how to figure it out. So any questions on that? All right, so we've got some various things that we've discovered, so on and so forth. And what I want to do now is I want to work a very straightforward example. And the example is, now this is somewhat like your book's example. So your book says when a family of 4 with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's springs compress 3.0 centimeters. A, what is the spring constant of the car's springs, assuming they act as a single spring? And B, how far will the car lower if loaded with 300 kilograms rather than 200 kilograms? So what I'm going to do is say a car, in other words, I'm making this my own version, right? So a car sinks by 4.0 centimeters when 300 kilograms of, I should probably, 300 kilograms of people sit in the car. A, what is the spring constant? And B, or let's say this. How much would the car sink? And I'm just meaning sink in a sort of metaphorical way here. How much would the car sink if 500 kilograms was put in instead of 300 kilograms? Okay, so that's part B. Solution. So we know that Hooke's law is going to apply. Like I said, Hooke's law actually applies to rods, 2x4s, piling, stuff like that. But we use springs usually because otherwise you'd have to use really large forces to even measure the amount a 2x4 would compress. And when you use large forces like that, it gets kind of dangerous. So what we have, at least in magnitude, is F is equal to KX. That's Hooke's law. When we don't care about direction, we can just use F equals KX. So what I'm going to do for part A is I'm going to say the F is going to be 300 kilograms times 9.80 meters per second. Hopefully that reminds you that mass is not a actual force, but weight is. So I'm going to do 300 times 9.8, and that gives me 2,940. And that's equal to K. And notice the units I have to do here. This is 0.040 meters. So if I solve for K, I get 2,940 newtons divided by 0.040 meters. And in this case, I get 7.35 times 10 to the 4th newtons per meter. So that's my spring constant. And I've tried, well, actually, no, I'm using one extra sig fig here. So I'll put a little blue underline there. And this will be the answer to part A. Okay, now part B, they want to know what is the compression, or what is the X when the force is actually 500 kilograms rather than 300. Well, 500 is actually 1 2/3 as much. And of course, 1 2/3 would be 5/3 as much. So we would expect the actual stretch to be 5/3 of 4 centimeters. So, and that's just because F and X are linearly related, or in this case, they're directly proportional. So if you double X, you double the force. If you increase the force by a factor of 1.378, then you increase the X by a factor of 1.378. That's just the way directly proportional quantities work. If it was KX squared, there'd be a different calculus where if you doubled the X, you'd actually quadruple the force. Or if you tripled the X, you'd actually nine-tuple the force. So in this case, our first order approximation is I can assume it's going to be roughly, so this is me just doing it on a whim using my understanding of the direct proportionality. I'm going to say X is actually equal to 5/3 times 4.0 centimeters. And when I do that, I can say 5 times 4 is 20. And then I divide 20 by 3. 20 goes into 18. Or excuse me, 3 goes into 18 6 times. And then I'd have 2 left over. So that'd be 6.666 centimeters would be the answer. Okay, so that's just one way of doing it. But I can also be a little bit more traditional, and I can just say F is equal to K times X. So that means I should take 500 kilograms, multiply that by 9.80 meters per second every second, and that's going to be equal to 7.35 with one extra sig fig times 10 to the fourth newtons per meter times x. And that would give me x is equal to, so 500 times 9.8 is equal to 4,900. So that's 4,900 newtons. And now I'm going to divide that by 7.35 times 10 to the fourth newtons per meter. So I'm going to divide the 4,900 by 7.35 e to the fourth newtons per meter. That gives me meters. And that gives me x is equal to 0.06667, like that. And technically I should have used an extra line there. So you can see that this is actually equal to 6.67 centimeters as well. So we got the right answer both ways. Again, feel free to do either way you want. But if it's something where you don't get to write out any sentences and all I can look at is the right answer versus the wrong answer, then you might want to take time to write out why you did it this non-traditional way. But by all means, the goal in physics is to learn how to solve problems. And the more ways you can solve it and get the same answer, the more confident you are with that answer. So anybody have any questions on that? All right, so that's just another typical problem. We'll see how we can do more of this a little bit later. What I want to do now is I want to go ahead and attack exactly what we mean by a simple harmonic motion. So I'm going to take Newton's second law of motion and I'm going to employ it. So Newton's second law can be written like this: the summation of the forces, that means the net external force acting on the system, is equal to m times d2r over dt squared, like that. Now, if we reduce that to one dimension, then that becomes the summation of the forces, let's say in the x direction, is equal to m d2x over dt squared. Okay, that could also just be m dv dt. That would be acceptable as well, but that's Newton's second law. So if I go to apply Newton's second law to this spring that's lying horizontally over a frictionless surface, then this would be more or less what the system looks like. And I would have a spring that comes out and then I'd have a mass on a frictionless surface of mass m. And this is frictionless. Oops, I didn't write that very smoothly. My I got run over. My I got ran over by another letter. And what I'm going to do is I'm going to set up my coordinate system so that the origin is actually at the center of mass. So at center of mass of m, while spring is in equilibrium. I can never remember if equilibrium is two L's or not, but I will solve that problem by abbreviation. As you can tell, what a couple days ago, oh no, that wasn't your class. I'm not going to admit my errors from one other class to this class. That would be crazy. But no, I was spelling a word wrong the whole during class. Didn't even realize it. Just being a goober. All right, so that's the coordinate system we're going to use like that. You can see if I pull the mass to the right, that's going to be a positive x. If I pull the mass to the left, that's going to be a negative x. And if I just leave the mass alone, it's going to be at x equals 0. So everything works really well. So when I go to actually apply Newton's second law, what I have is m times d2x over dt squared is equal to negative k times x. And the negative, of course, has to be there because you realize the force has to act in the opposite direction of x. So if the x is a positive, then the force has to pull in the negative direction. So you really need that. Well, that is a differential equation, but there's a better way I can write it. And that's going to be, first, I'm going to put both terms on the same side of the equation. So I get m d2x over dt squared. And then when I pull the kx to the other side, it becomes a positive. So it's positive kx and it equals 0. But now I'm going to divide through both sides by m, and I get d2x over dt squared plus k over m times x is equal to 0. This is the differential equation for the simple harmonic motion. Okay, so it's simple harmonic motion. Whoa. Simple harmonic motion differential equation. So this is something I want you to commit to memory because it's something that can come in handy over and over again in a bunch of classes, because every time you see a differential equation like this, you can immediately know exactly what the solution to the differential equation is. So there's my abbreviation. Let's see this. There's another abbreviation. So I want you to commit it. And I will tell you that if you were taking differential equations, they would tell you this is a second order linear ordinary differential equation. It's second order because the highest order derivative that's done is a second order. In other words, you've taken double derivative. So that's what makes it second order. It's linear because there's no x times or there's no derivative of x times a derivative of x. And I'd have to double check to be sure, but I also think you're not allowed to multiply x times a derivative of x either. And it has basically constant coefficients, so that's helpful. And in fact, the way I've organized it is the leading term has no coefficient, and the term that has no derivative in it just has a single coefficient, which in this case is k over m. And that's going to come in handy. Now, if you took this in differential equations, what they would argue is, wouldn't it be wonderful is if there's this function x of t that when you took its derivative, you would get the exact same function back, but maybe it'd be multiplied by a number. In other words, it's what we call an eigenfunction of a derivative operator. And that is nice. Can anybody think of a function that you take the derivative of and all you get back is the original function times maybe a number? Even if the number's 1, that would be acceptable. But can anybody think of a function like that? How about this one? Okay, x of t is equal to e raised to the at power. Dx dt, which by the way, a lot of times we use this notation. It's just x with a dot over it. Can anybody tell me what the derivative of e to the at is with respect to time?
Is it e to the at times a?
Yeah, exactly. So you see, this is exactly one of those eigenfunctions of the differential operator. In other words, when you take a derivative, you get the same thing back, but with a eigenvalue or a number in front of it. So this is a case in point. And in fact, that's what they'll teach you in a differential equation class. They'll say, okay, well, let's let the function be x equals some number, let's say C1 times e to the rho t. and the rho is possibly a constant. It's possibly well, it's almost always a constant. But then your job is to figure out what that rho is. So you could do that, and what would happen would you would actually get a result that's pretty good. You get some positives and negatives for the rho and all sorts of stuff like that. But in physics, we can handle it a little better than that. For instance, I suspect this thing's going to oscillate back and forth and have what we call simple harmonic motion. And because of that, I know it's going to act like a cosine or a sine function. So I'm going to make a what Einstein would have called a Gedanken. Which is a guess or a thought experiment type of thing. And I'm going to say, let x of t be equal to a cosine omega t plus phi. Now, let me give you a little bit of argument for why this is it. For starters, the cosine, I think that part should be pretty straightforward. Of course, I could have equally well written sine, and that would be fine as well. I could have written sine omega t plus phi. But what I want you to know is this differential equation is something we're trying to solve. We're trying to find out what x is, okay? And what we have is x, but we also have sometimes a first order derivative of x, sometimes a second order derivative, sometimes a third order, all sorts of stuff like that. So what we really like to do is undo those derivatives. What operation undoes a derivative?
Integral.
An integral. In fact, when you first learn it in calculus, they usually call it an antiderivative, right? So if it's a second order differential equation like this one is, how many integrals do you think you'd need to do to solve it? If you integrated d2x over dt squared one time, that's the same thing as integrating dv over dt one time, and you get the velocity, right? But then the velocity is dx over dt. So you'd set that velocity equal to dx dt and integrate it again. So everybody see that you are going to integrate twice? Does that make sense to everyone? Okay. What happens when you just integrate a function without necessarily knowing the range of integration? There's something you got to include. Do you recall what that is?
Constant.
Yeah, integration constant, right? So if you got to integrate two times, that means you expect two integration constants. That means you should have at least two parameters. Free in your answer. Now, in this case, I have three parameters. I've got A, I've got omega, and I've got phi. Well, what's going on there is I suspect there's a parameter that's going to be decided based on just the fundamentals of the problem. You know, the problem is we have a spring with a spring constant K with a mass on it whose mass is M. So I suspect the K and the M might ultimately determine one of these constants. And then I still need the other two constants to make up for the integration constants. And the integration constants are made up by what we call initial conditions. Initial conditions can determine 2. So what do we mean by initial conditions? We could say something like x of t equals 0 is equal to a, and we could say v of t equals 0 is equal to 0. Those are true initial conditions because they occurred at t equals 0. But we would still call them initial conditions if I said x of 4.5 seconds is equal to 1.2 meter and v of 3.78 seconds is equal to 1.5 meters per second. Those are initial conditions as well, even though, like I said, they're not really initial. So I'm not sure if a mathematician would call those initial conditions since they're not at t equals 0. But what I'm trying to tell you is in the physical world, you're going to need 2 expressions to allow you to determine the 2 unknown constants. And those 2 expressions could have also been x at 4.5 seconds and x at 3.9 seconds. It didn't have to have a velocity at all. Okay. But that's the main thing I'm trying to say here. So that hopefully sets you up to where you have some understanding of why we have to do what we have to do. So now that I have that, I'm going to go ahead and take this hypothesis function and compute the derivatives. So let's try our, and this is what Einstein called it, our thought experiment. The Gedanken that I was talking about. So we said x of t is equal to a times cosine omega t plus phi. And right now, we don't necessarily know if that omega has anything to do with angular frequency or angular speed. All we know is it's another symbol. So right now, we don't know anything. It will turn out actually to be an angular frequency, but that we don't know that yet. So let's first off try dx dt, which, as I said, is also called x dot. When I take the derivative of x with respect to t, the derivative of cosine is negative sine. So I'm going to get a negative. I'm going to get an a because the a was already there. And that's going to be a sine of omega t plus phi. Okay. Now I've got to take the derivative of omega t plus phi with respect to t, and that's going to give me omega. Now I got to take the second derivative. So the second derivative of x with respect to time, that's equal to x double dot. Okay. And now that's the derivative of x dot. So the derivative of sine is cosine. So the negative is going to stay. I know the chain rule is going to give me another omega. So I'm going to say it's omega squared a. And now I'm back to cosine omega t plus phi. Like that. So now all I have to do is plug them into the differential equation. So plug them in. And what I get is negative omega squared times a cosine omega t plus phi. That's for the d2x plus dt squared plus k over m. Now I got to plug in just the plain x, which is a cosine omega t plus phi. And all that is equal to 0, which I can simplify a little bit by writing negative omega squared plus k over m times a cosine omega t plus phi. Now, what this is Newton's second law. This equation is exactly the equivalent of Newton's second law. It's also called the equation of motion that we often are trying to solve for. But the main thing is it's Newton's second law of motion. It's not Newton's helpful hint that sometimes works. So what that means is this equation has to be true at all times. So has to be true at all times t. Okay. So that means we can't choose a specific omega and a specific phi to make a cosine of omega t plus phi equal to 0, because that would only apply for that one particular time. We can't use A equal to 0 because we know that's ultimately going to turn out to be the amplitude, and the amplitude being 0 is not helpful. So in fact, what we have is we have to take the other part of the equation and set it equal to 0, and that gives us negative omega squared plus k over m is equal to 0, which means omega is equal to the square root of k over m, which means, as expected, the omega turned out to be a value that was dependent on the very structure of the differential equation, the very structure of the problem for that matter. So that means literally, because we had a spring whose spring constant was k, and because it was lying on a frictionless table with a mass m, then the omega in our A cosine omega t was predetermined to be the square root of k over m. We've got no way to get around that. So that's really what our big solution is. It's just a matter of, oh, it's going to be omega equals the square root of k over m. Then I have to use my initial conditions to figure out other stuff. So, for example, what if, let me see, let's say, what if the mass started at a maximum displacement A. Now, what we mean by this is I'm calling it A, and A is already in the equation, but we could mean A equals 2.3 centimeters, okay? Meaning I'm talking about a very specific number here. And since I said it started at that, this translates to x of 0, which literally means x of t equals 0, is just equal to A. So that's one of the initial conditions. And I'm saying, what if the mass started at a maximum displacement? Oh, no, didn't mean to do that. Now I'm going to put this all in curly brackets. The maximum displacement A. And let's say, and was released. So was released is, again, some code words for some equations. And what we mean when they said it was released is just like saying a ball was dropped. What can we infer about a ball that was that had been dropped? Anyone? The ball was released from the height of a building. What do you know about that ball?
Like, what are you asking exactly? Like we're using like free body motion equations.
Yeah.
And all?
Like, what kind of parameters from kinematics do you know? You know acceleration? Do you know initial velocity? That kind of stuff?
Yes, you know, initial velocity would be 0, and
Exactly.
initial
That's the
acceleration
part
would
I
be
was shooting
rapid.
for. So yeah, that's the part I was shooting for, was the initial velocity is equal to 0. So what that means in terms of equations is v of t equals 0, which is v of 0, is equal to 0. So that's what we've got here. So when I do this, I'll say x of 0 is equal to A, and v of 0 is equal to 0. X of 0 equals A means A is equal to A cosine And I don't have to do it this way, but I'm putting it in here just to remind you guys that we do in fact know what cosine or what omega was. And then plus phi like this. Only let me back up a bit and remind you that yes, we know what omega is, but in fact, this is at t equals 0. So we have a 0 there. And this implies A is equal to A cosine phi. Similarly, we had done V. Remember, V is equal to dx over dt. And what we found is V was negative omega A times sine. So I'm going to put 0 here is equal to negative omega A times the sine square root. Again, don't have to write it this way. I'm just wanting to remind you guys that we do in fact know it. And this is plus phi. Okay. So in this first case, we could say phi could equal 0, but it could also equal plus or minus it could also equal plus or minus 2 pi. Okay, because what we're wanting is the cosine to be equal to 1. Cosine's 1 at 0, cosine's negative 1 at pi, and cosine's 1 again at 2 pi. And now if I look at this other one, what I have is negative omega A is equal to negative omega A times the sine of phi is equal to 0. If you look at this and say, wait a second, if I do use phi equals 0, like is one of the choices for the first part, then the second part automatically becomes 0 too. So now I'm going to say, let's choose this guy. Or to be honest with you, you could have done 2 pi as well, but the 0 is the simplest one. So now I'm going to say phi is going to be equal to 0. And that gives us basically exactly what we want. We can now say that x of t is equal to A times cosine square root k over m times t, like that. And that fits both of those initial conditions. Does that make sense? Another one is, let's try another example. What if at t equals 0, you hit the mass? So let's say at t equals 0, you smack the mass with a hammer so that it starts to move to the right, which is the positive x direction. Well, if that's the case, then what you're saying is x of t equals 0, which we also call x of 0, is equal to 0. And what we say is v of t small. So what I'm saying is t is slightly bigger than 0. That should equal a positive velocity. Okay, because I'm told you that it's going to be hit while sitting still right at t equals 0, and it's going to be pushed in the positive x direction, so that the velocity right after t equals 0 is going to be in the positive direction. So what do we get from that? Well, I can say 0 is equal to A cosine omega, which we already know. Oops. Omega times 0 plus phi, like that. And in this case, I would want to do, because you wouldn't want to do it with the A, because that's basically an arbitrary solution that wouldn't help anybody. But if what you need here is the cosine to be 0, and the cosine is 0 at plus or minus pi over 2, and again at plus or minus 3 pi over 2. and then a bunch of other values like that. Okay, so that's some of the solutions. And now the velocity should be positive. So I'll say this quantity is greater than 0, and I'm going to say it's negative omega A times the sine of omega t plus phi. Okay, that's what the velocity is. Remember, when you take the derivative of x, you get negative omega a sine omega t plus phi. And I'm trying to consider for t greater than 0. And we know what sine looks like if you actually make a plot of sine of t versus t. What you get is this, and of course it's odd function, so it's exactly the opposite to the left. But from 0 to 90 degrees, you see that's going to be positive. What we need is the sine for a small t. We need that to be a negative value. If I used pi over 2, I'd get 1. That's not helpful. If I used 3 pi over 2, which would be right here, I get negative 1. So this suggests between this guy and this guy, phi equals positive 3 pi over 2 might actually work. So what I would conclude in this case is that x of t is equal to a cosine square root k over m times t plus 3 pi over 2. And that will actually meet the criteria for these initial conditions. Does that make sense? All right, now let me ask you something really quickly. Here's another example. If we find simple harmonic motion is described by x of t is equal to a sine of 8.0 t plus pi over 2. Actually, let's not do it that way. Let's do let's say we found that x of t is equal to 3.0 centimeters times cosine of 7.0 radians per second times t plus pi over 2. Oops, I want plus pi over 2, and I want that to be in square brackets. What is F? That'd be part A. And then part B, what is T? And then part C, what is the maximum the spring stretches? Can anybody tell me how to start part A? Or give me some idea how to solve this? That's the general answer for the simple harmonic motion is x of t is equal to a cosine omega t plus phi. And I've told you the very specific answer, which is 3.0 centimeters cosine 7.0 radians per second times t plus pi over 2. So can someone tell me how we're going to find F? Anybody?
So would you use the angular acceleration to
Yes.
find f?
Do you
So you
know
do
what the angular acceleration is?
2 pi, well, it would be 7 divided by 2 pi would give you f.
Okay. So yes, that's exactly right. Because what I'm trying to say here is, and I don't know why it keeps doing this, but I'm trying to write 7.0 radians per second times t plus pi over 2 like that. So yes, what we found is that the omega is equal to 7.0 radians per second, but that's also equal to 2 pi f. So f should be 7.0 radians per second divided by 2 pi, which gives us 7 divided by 2 times 3.14159. That gives me 1.11. And that would be hertz. How about part B? How are we going to find the period now?
It'd be 1 over f.
Very good. Yes, T is equal to 1 over F. So I'll do 1 divided by answer, and that gives me 0.898. Getting 1 extra sig fig, and that's in seconds. So we've got that answer as well. And how about part C? That one should be the easiest, hopefully.
Plug it in.
The C was what is the maximum spring the maximum of the spring stretches? So the maximum it's going to stretch is 3.0 centimeters. Does that make sense to everyone?
And that's because that's the amplitude, right?
Exactly.
Yeah.
Yeah, it's going to go from the equilibrium all the way to positive 3 centimeters, back to the equilibrium, then all the way to negative 3 centimeters, then back to equilibrium, so on and so forth. So the maximum it ever stretches would be 3 centimeters. That makes sense? Now you can look at examples like example 14.3 where they investigate the car again. They say determine the period and frequency of the car after hitting a bump. Assume the shock absorbers are poor, so the car really oscillates up and down. What we learned before from that same car was that the car weighed 1,200 kilograms, and then we added another 500 kilograms to it, right? Or I think the first time I added 400 kilograms, something like that. The main thing is that I'm going to take that new mass, which is the mass of the car plus the first mass of people that I put in it, whatever that was, and that's the new mass, and that gives me my omega is equal to the square root of k over m. But in this case, we already know the k, and now we know the m, so we can actually get omega, and we want to know what the frequency the car is going to oscillate at. Well, that's easy enough. I'm going to take the omega and divide it by 2 pi. And if I want the period, now that I have the frequency, I just take the reciprocal of that, and that gives me the period. So you can do that with example 14.3. You can do the same thing with example 14.4, where you have a spider web. In that case, they're saying a spider has a mass of 0.3 grams and it vibrates at 15 hertz. And they want you to know what the spring constant is. Well, it vibrates at 15 hertz. So omega is 2 pi times 15. But omega is 2 pi times 15, and omega is also equal to the square root of k over m. You know the m is 0.30 grams, so all you have to do is solve for the k, and that'll give you the spring constant for the web, assuming that it actually behaves that way. And then at part B, it says at what frequency would you expect it to vibrate if there was an insect on it with an additional mass of 0.1? So now you're going to go back and do the same thing using the same K, but this time changing the mass from 0.3 grams to 0.4 grams. So I will do that next time, but I just wanted to give you a way of walking through that, and we'll finish this up in our next meeting on Monday. So you guys are free to go. I will remind you to make sure you check out examples 14.3 and 14.4. So I will say that here. And I'll wait for the last person to leave. Alyssa, Abigail, you guys have any questions? Sorry, I didn't have the chat open this time. It looked like Mika was answering some questions and I missed it. Apologize for that, Mika. Alyssa, it seems like you might not be here. You still here? All right, I'm going to call it a day. Have a good one, everyone.